All right, so section 6.4 is all about proving circle conjectures. So we're going to look at one conjecture specifically today. And it is the inscribed angles or inscribed angle conjecture. However, this conjecture is a bit unique, is because there are actually three different cases that we're going to have to prove. Even though it's one conjecture, we're going to have to create three proofs. Now here's why. We know that when we prove something to be true, we have to prove it to be true for all possible cases. That means that we have to prove that every single possible inscribed angle has a measure that is equal to half the measure of its intercepted arc. Well, we couldn't possibly take the infinite number of inscribed angles that are possible, right? But what we can do is we can actually classify all of those angles into one of these three cases. The first case is when the center of the circle lies on the inscribed angle. The second case is when the center of the circle lies outside of the angle. And the third case is when the center of the circle lies inside of the angle. Now today, in this lesson, we're going to prove case one only. All right, we're going to start by brainstorming the argument of this proof. We have an inscribed angle here. Let's call it angle ABC. The measure of angle ABC, we don't know the actual measure, so we'll just call it X. Now we need to prove that X is equal to 1/2 the measure of arc AC. So drawing radius from the center of the circle out to point A, and we now have created a second angle up here. Let's call it Y. And we also have created a central angle here that may become important, right? By drawing in radius A, we can certainly call that O, circle O. AO is a radius. BO is a radius. Those are congruent, thus creating an isosceles triangle, ABO, down here. Okay, so we have central angle AOC, whose measure is Z, right? It doesn't have a specific measure, we're calling it Z. Now we know that Z, the measure of the central angle, has to be equal to the measure of its intercepted arc, which is arc AC. So that certainly is true. We also know that since we have isosceles triangle ABO, that the base angles are congruent. Now X represents the measure of one base angle, Y represents the measure of the other base angle, and if the angles are congruent, then we know the measures are equal. So we can say X equals Y. Not only is Z the central angle, but it's also an exterior angle to triangle ABO. And by the exterior angle theorem, we know that any exterior angle is equal to the sum of the two remote interior angles. Well, here the two remote interior angles are X and Y. So we know that Z equals X plus Y. Since X is equal to Y and Z equals X plus Y, we can substitute X in for Y and say Z equals X plus X. Then we can combine like terms. Z equals 2X. Then we can solve for X by dividing both sides of this by 2. Those cancel. So X equals Z over 2, which is the same as 1/2 Z. So we can finish this by simply taking the fact that z equals the measure of arc AC and substituting it in right there, right? So there's the argument of our proof. Now, creating the argument is not the same as writing the proof, right? We have not written a proof yet. That's the next step. So we have our diagram in the top right corner. Now we need to start writing the proof. So we may start by saying angle ABC is inscribed in circle O. That's given information. That would lead us to say x equals the measure of angle ABC. And, I mean, that's just from the diagram. So we could probably say that this is given information too. In fact, we may even be able to leave out that first box and just start with x equals the measure of angle ABC. But we'll leave it there for now. So AO is a radius of circle O. Definition of radius. All right, so AO congruent to BO. Arrow there. All radii of the same circle are congruent. So triangle ABO is isosceles. So this would lead right down to here, and that's definition of isosceles triangle. All right, so now we have the isosceles triangle, so now we know that x equals y, isosceles triangle theorem, and that is definitely coming down from there. So z is the measure of our central angle AOC, so we can say that z is equal to the measure of arc AC by the definition of arc measure. So we know that z is equal to x plus y because z is the exterior angle to our triangle, and this is the exterior angle theorem. So we can definitely connect these. Basically, since we had our isosceles triangle, z is an exterior angle of the triangle, so we can connect those with that arrow. So now we're going to substitute x in for y, and we're going to get z equals x plus x. And that's coming from this box and this box together, and that is the substitution property of equality. So next we can combine like terms and say z equals 2x. Combine like terms. Then we divide both sides of this equation by 2, and we get x equals 1/2 z, or z over 2. You could write it either way. They mean the same thing. And this is the division property of equality. So the only thing left is to substitute our angle and our arc measure. So we'll have x becomes the measure of angle ABC, and that equals 1/2 of z, but z is now going to become the measure of arc AC. And this comes from here, and from here, and from here. And that's all the substitution property of equality. So, we are now 1/3 of the way done with the inscribed angle conjecture proof. Right? We have proven case 1. We will have to prove cases 2 and 3 in order to prove the theorem.